Hello and welcome to Statics for Mechatronics Engineers. I'm Nyasha. I hope that we will have a cool ride as we work out some problems to see what happens when an object is in static equilibrium. The study of mechanical objects that are in static equilibrium. That is all we are doing in statics. This lecture is an introduction to what we are going to be delving into this semester. I will briefly summarize the administrative material, the administrative part, and then we will move to the fundamentals of the theory that we will cover. That is labeled Statics Fundamentals. The details that you see on your screen, on the module, the delivery, the class, the textbook, and my details, I suppose you already know that. So having gone through your Moodle page, I think you've seen something called the study guide. Please go through that because it will summarize the long and short of what we're doing here. Right, so statics is a module specifically for mechatronics engineers. It is studied by many other departments, but the topics that we have extracted for you, chapters 3, 5, and 9, those topics are tailored to shape your mind to think in 3 dimensions as far as objects that you will electronically control when you are in your control modules are concerned. Right, this module is brought to you by the physics department. We already know that. The module code is FMEV 102, specifically for engineering, but generically on Moodle it is labeled FME 102. The material is exactly the same. It being FMEV 102 statics simply means that this is the same module as far as the content and the marks are concerned with your electricity and magnetism. The marks that you will get at the end, which are made of the content in electricity and magnetism, and what we will learn. Those marks will be combined and you will get your result for both efforts. However, the statics material, the theory that we will study, is basically mechanics. So when we look at mechanics, remember what we were studying in FVV 101. That's what we are building on. In FVV 101, however, we were studying the mechanics of particles. We were studying particle mechanics. We assumed that something as large as a vehicle, something as large as your arm, something as large as a building is just a particle on which we would draw its weight and we would draw some reactions and then we would analyze for the unknown. But this time statics is trying to tell us that objects are made of those small particles put up together to make what is called a rigid body. So obviously there are other non-rigid bodies. We are studying only rigid regular shaped bodies. So the equilibrium condition is basically what we are trying to figure out. I'm Nyasha, you have my details, and we are studying online, so everything is being done on Moodle. We will meet on MS Teams and we'll have tutorials on YouTube. We will study in this month of October, finishing up October until November. November 12th is our last day of meeting. Then we'll write our assessments according to the timetables that you've seen. This page basically summarizes what we are going to cover this semester. The statics module covers 9 lectures, 8 tutorials, 4 practice tests, 2 tutorial tests, and 1 semester test. The 4 practice tests do not contribute to your marks. These are practice just to give you an idea of the stuff that you'll be asked. They also are to test your speed, so you are given, let's say, 5 attempts to run the whole set of questions. So it is good practice. If you do it the first time and you get 100%, but you got it in an hour. Try to beat that by 10 minutes and so forth, so that you can be fast at your thinking and your problem solving. So that is the content that we'll cover. Everything is summarized on the Moodle page. On the Moodle page, you've got a section on general information, learning resources, the chapters, which is the actual content, then your tests, your assessments, right? Right, so what I'll just discuss on this page is basically the material that you find on your Moodle page, and the philosophy, which I think can be useful for you to be able to attempt your statics material. Right, so as far as the general information is concerned, you already have seen that this is just a section for your announcements and so forth. So there's a small chat that we put there. The idea is for us to interact. You can make use of that from now. It's already open, so which means it's subject based. If you're asking a question about something and someone has an idea, it should pop up on your phone, because it's just another, it's on the Moodle platform. Right, so on that chat group, let's make use of it. Let's obviously respect the etiquette, communication etiquette that is recommended by the varsity. Then we've got learning resources. So there's a very nice table there that summarizes the data sheets that are necessary for this module. So make use of that. The chapters have the content and the lectures. So for instance, for every lecture link, you've got a link to the MS Teams meeting. So if you did not get the email, you can just click there. The script preparation is something that I would like to just recommend for your test. So these two tutorial tests are written online. You're going to be selecting some answers, or you will be typing some answers. So everything is submitted online. It is marked by the Moodle system, and then you get your results. However, the semester test is it's a way we want to examine and see your writing. You need to communicate the engineering or the science solutions that you're coming up with. So this semester test is written. You're going to write and submit a script. You're going to submit a script. So this is just a guide. Please submit a single and a legible PDF file. Single PDF file, legible as in if you are using a camera to take photos of your script, make sure they're crystal clear. Then make it a PDF file. Please do not submit your test, your semester test, as a Word document or a picture or a JPG or other file name. Your naming convention of the file is exemplified here, so you can put your surname in caps, dash, and then semester test, just an ST for semester test. For example, here I put my name there, Suliali, dash ST for semester test. That's the full name of the semester test script. Right, as far as the philosophy of studying this module is concerned, this is just a recommendation. Our studying habits are different. So I think that this module is a bit special because, number one, it is mathematically demanding. Number two, it is interesting because it is applicable. You will see that the applications of statics are our day-to-day bread. You will see objects that you use, or objects that you've seen being used or installed in different places. So each chapter and each set of questions will have draftsman drawn objects. So the applications are exciting. Now, for you to understand that stuff, you will need quite some time, like a normal module time, like a semester. But we are doing this in just 3 weeks. So we are studying everything in just 3 weeks. This means in the next 3 weeks, the main recommendation I give to you is you need to diarize. You need to be on top of this. Let nothing go past. Diarize and plan that on this day, I'm going to study this, and please prepare. So study ahead. Don't wait for the lecture to start and then you start trying to follow what you're trying to study. Please attend the lectures as best as you can. Fortunately, we met yesterday to test our system, and we discovered some problems on my side. So in case we have problems such as connectivity, or we have problems such as electricity supply, we are going to make sure that in 5 minutes, if the lecturer disappears from the system, there's no message on the chat where I'm saying that I've got a problem with the connectivity, I'm going to reconnect or whatever it is. In 5 minutes, you are dismissed. You can study and do other things. I will then record the lecture and then post a pre-recorded lecture. So, which means you will need to attend, yes, but in the event that we've got some connectivity trouble, then we are covered. Now, please have the habit of writing. Please have the habit of writing. This module, it requires you to get used to solving the problems. When you write something, you get to remember. I hope that we do not sit and just watch a lecture as it goes. So please have the habit of what? Of writing. When you're writing and you get stuck somewhere, ask. So when we come for the lecture, the idea is in the first 1 hour, we will go through the material in some chronological order that is given in the textbook. The questions section, the last 10 minutes, is for us to attend to questions. So while we are in the lecture on MS Teams, you can type your question. And then when we are done with the lecture and we've got the material now, then I can attend to certain sections of I can attend to the questions. So the idea here is an interjection. Sometimes it can come as a question that is going to be answered later. So I would prefer that we hear the whole story and then we can ask. However, there are some reasonable interjections where, for instance, I have written something that is actually incorrect. So please insist. You can keep raising your hand on MS Teams so that we correct something. Right, so please ask. I look forward to lots of questions. Then experiment, right, at home. Try this. This is statics, right? These are objects that are in static equilibrium. So you can do this at home, right? Most of the stuff you can try it at home. If we are talking forces in an object that is in static equilibrium, the idea is, let's say we are looking at a seesaw, right? You can actually make one. You can just take some wooden plank. You can take some object to make a pivot and see how to balance this thing. So it will be applied in some section. So experiment, also try these things at home. Of course, not the dangerous ones, right? Okay. So attempt the questions. There are plenty questions to do in your textbook. The textbook has got simple problems, then it has the end of section problems and the end of chapter problems. So please attempt as many problems as you can, if possible, before the lecture, right? The lectures are itemized into chapters. Attempt some of the questions, even if we have not done the material, so that you can just try any method, just try and see what comes out. So attempt the questions, attempt the problems, list your questions so that you can ask, and then revise. So right now, my assumption is, from what was described in the study guide, you guys have already started revising your FVV 101. So just out of interest, you should know by now which chapters in FVV 101 or in Survey that are relevant to this module. They are just 2 chapters. Okay, so that covers the fundamentals. Right, so administratively, we are done now. Anything else we can discuss as we go in the lectures. So let's jump now into the theory. The following is going to cover the fundamentals of statics. So scientifically, studying an object that is non-accelerated takes knowledge of the forces that are acting on it. So in statics, you will notice that mechanics is basically branched into particle mechanics. We've got rigid body mechanics, we've got deformable bodies, and we've got fluid mechanics. Now, we are focusing only on rigid bodies. So we are not worried about deformation. So don't worry about the chapter on young modulus and so forth. We are not talking of fluids, whether it's Bernoulli effect and stuff. We are just looking at rigid bodies. Rigid bodies can be studied in terms of statics or dynamics. So you will notice that this is what we focus on, so that next year, when you're second years, you can qualify to study the dynamics module. The material that we are studying, please do your best to have an understanding of it in the simplest way possible, so that when you are in dynamics, it will be assumed knowledge. So some of the material may be a bit heavy. If it's assumed knowledge and you have not grasped it, it might work against you. Right, so the chapters that we will cover are summarized as follows. We will study force systems, chapter 3. We will study centroids and centers of gravity, chapter 5. We will study moments of inertia, chapter 9. These are suggested prerequisites, so we will actually cover chapter 2 today in this lecture. However, if you are to cover chapter 5, please just browse through chapter 4. Just browse through, just look at what is being discussed in chapter 4. It can be of use to you. Then the fundamentals for chapter 9 are chapter 5, and we're going to go through it, so we're good. In chapter 3, obviously we've got the subtopics there. It's basically forces and moments, turning effects. And then in chapter 5, we've got centroids and centers of gravity. So the most important is obviously the center of gravity, or the centroid of three-dimensional objects. Then you've got moments of inertia. This is very, very important. Radius of gyration. So if I would give you a hint as to the most important things that I even got a recommendation from Prof. Bota about, please, the radius of gyration and the moments of inertia. Master these concepts. This is what you will need to use in dynamics later on. Right, so we've summarized the topics that we will cover. Chapter 1 of this textbook by Beer and Company is a very important chapter. It lays the rules. So we are not really covering chapter 1 as in we're going to be examined on material in chapter 1. It's assumed knowledge that is embedded in chapters 3, 5, and 9. So chapter 1 is cool because it gives you what are called the 6 fundamentals. What are the 6 fundamentals of mechanics? The first fundamental of mechanics is the parallelogram rule. So you will notice that with the parallelogram rule, all we are attempting to describe is vector addition. For us to find the resultant of 2 vectors acting at a point, there is a rule that was introduced to us in mechanics called the parallelogram rule. So that parallelogram rule basically states that 2 vectors that are acting at a point, let's call that point O, such as vectors A and B shown in that sketch. These vectors have a resulting effect that can be found by plotting a parallelogram formed by the vectors. Then you find the magnitude of the diagonal of the parallelogram to then deduce the resultant. So the parallelogram rule simply suggests that if you have 2 forces, take the one force and plant it on the tip of the first force. So we are planting force B on the tip of force A. We are planting force A on the tip of force B to form a parallelogram shape. The parallelogram rule now says the resultant of these 2 forces is the geometrical diagonal of the parallelogram. By the way, this law cannot be mathematically proved. this is pure experiment. So it's science, it's physics, and it's applicable in many places. And it is one of the most fundamental rules of mechanics, finding the resultant of two forces using the parallelogram rule. The second fundamental of mechanics is what is called the principle of transmissibility. The principle of transmissibility. You will make use of this principle. This principle simply states that a force acts on a certain line of action. When the force is acting on a body, one can find the effect of that force by drawing or plotting the force along the same line of action, but at any point along that line of action. So you've got an object. There is a force that is acting on the object at point A of the object. The principle of transmissibility says this force F can be transferred or transmitted to any point along the line of action of that force to derive the same effect as the force at its initial point of application. This simply means that when you are dealing with forces, you can move that vector, that force vector, along that line of action to any convenient point, and you will get the same effect. Remember, you are using this as a principle of solving problems in mechanics. So it's a second fundamental called the principle of transmissibility. You have used it before, but maybe it was not defined. So basically that's it. The third set of fundamentals are actually three laws, the Newton's laws. So the third fundamental is basically Newton 1. Every object remains in its state of motion or rest unless an external force acts on it. Then your fourth fundamental is your Newton 2. The net force that is acting on a body is directly proportional to the acceleration of the body in the same direction. Then your Newton 3, action and reaction are equal and opposite. That's your fifth principle. The last principle is the principle of the gravitational force, basically telling us that the objects that we are studying in mechanics are all objects that have some mass. If these objects have some mass, these objects are always attracted to the center of the earth by this force called the gravitational force. So with all our analysis, we will make use of the gravitational force. Usually we will make use of it inside Newton 2 to describe the weight of some objects as mg in a certain direction. So basically these are the 6 fundamentals of mechanics which you have used and will use throughout this module and elsewhere. The second important thing covered in chapter 1 are prefixes and systems of units. Prefixes, we've already made use of prefixes several times. So for instance, when we are writing our forces, we write our forces either in newtons or we will write our forces in kilonewtons. We write distance in meters, we can write it in millimeters, we can write it in centimeters, we can write it in kilometers. So these prefixes, which you've studied already in mechanics when you started on units and measurement, we are going to make use of them a lot. Now, what is important in statics is for you to pull out the necessary prefix. You need to match the prefix to the situation or the condition or the object that you are studying. Let's take an example. If we are measuring the distance between 2 points along this pen, what is the most reasonable unit of measurement? It's obviously the meter. But what is the most reasonable prefix to apply to that? If you are measuring this in meters, you're going to bore us because you're going to say it's 0.0.0. So use the right prefix, use centimeters, because that way we can easily relate. Oh, it's 10 centimeters, so we can count. How about measuring the distance between Port Elizabeth and Johannesburg? Instead of you telling us in centimeters and you tell us it's 2 million centimeters, you should tell us in kilometers, because we can easily count and relate, and we say, okay, if it's 2,000 kilometers, okay, that's a lot, 2,000, right? So basically that is the magnitude. Obviously I'm wrong, I'm just giving you an idea of what you should use when you are deciding on the appropriate units, however, appropriate prefix. However, on Moodle, when the worst comes to the worst, you can use E. Let's say your answer, you want to write it in kilometers, you can use 1E3. Moodle understands E as your scientific notation times 10 to the whatever digit you put after it. So your principle of prefixes still applies. Systems of units. We have 2 systems of units that we will focus on. The SI unit system, we already know it, no need to discuss about it. Basically measuring our mass in kgs, our distance in meters, and so forth. However, there is a new system of units that you need to be familiar with, which is the imperial system of units, where our weight is now discussed in terms of pounds. Our lengths or our distances are now discussed in terms of feet, right? And so forth. So this system, there are already conversion systems. So there's a table in chapter 1. Go through this table. The idea that we're going to use is we need to have an idea of the system, because statics for engineers is applicable in many places. We are going to need to work with objects and systems that are designed in other countries. So worldwide, there are 2 main systems of measurement, which are the metric and the imperial. So one of you is going to graduate, you're going to go to the US, for instance, where weight is discussed in terms of pounds and distance is discussed in terms of feet. One of you might actually be working here in South Africa, or you can be in any other country that uses the metric system. But there are certain industries that strictly use the imperial system regardless of where you are. One simple example, go to the aviation school. There's a flight school right here in Port Elizabeth, and ask them the system of units that they use. You will notice that the average aircraft maintenance engineer or technician moves around with their tool tray that has got some tools that are both in imperial and metric. So the imperial system, because it is the one that is recommended or that is made use of by the Federal Aviation Administration. So you will notice that their systems are all measured in what? In feet and pounds and so forth. So you need to be familiar with it. So for us to be safe, what we will do in this module is we will make use of these units, but we are not going to need to convert them between the SI and the imperial system. So which means all you need to do is to just master the idea that, okay, if I have 1 kip, then it means I just have 1,000 pounds. So just get used to the conversions so that you can speak the language of that imperial system of units. So these are some of the basics that you need to master. This one is already described in the textbook, the SMART technique of solving problems. I usually like to simplify it. Right? So basically, when you're solving your problem, you need to divide all these stages of solving the problem by, first of all, listing your given data. So you list your data, and obviously the second step, you need to sketch. The sketches that you will be given here are usually draftsman drawn, so you are likely to have to derive a free body diagram from the draftsman drawn diagram, instead of you having to struggle with technical drawing some 3D object. Then you'll have to just figure out your free body diagram. So obviously, number 3, the equations are the most important. So you need to pull out the necessary equation, and if you have it, then you can substitute, substitution of your values. Then if you're done with substitution, then think, right, and analyze what it is that you're supposed to do, and if your answer really makes sense. So basically that's the last stage. So this is why I call it LI. I just put this just for you to probably try and remember the stages that you will need to go through when you are solving the problems. Statics is mostly problem solving. So it's principle, so that we get the technique of how some object works, what laws apply, then we solve problems. Right, significant figures, obviously, we have made use of those in the past. In statics, we are going to focus on just two laws for your significant figures. So these are obviously for you to write the final solution. You can study this description in chapter 1. The summary of it is, when you're writing your answer for all our statics problems, the significant figures rule that you're going to use is as follows. Number 1, if the answer starts with a 1, if whatever answer you're writing starts with a 1, it must have 4 significant figures. If your answer starts with a digit 1, it must have 4 significant figures. If your answer starts with any other digit that is not equal to 1, if it starts with a 2, a 0, a 5, and so forth, it should have 3 significant figures. So if my answer is 155, for example, I should write my answer as 155.0. It can be feet, it can be meters, whatever it is. But if this answer is 255, my answer should be written as 255 feet or meters or whatever it is. So basically, that is the convention. When you're typing in Moodle, respect this and use the correct number of significant figures. Those are all the rules and laws that you need to remember. So we are done with the basics in chapter 1. Now let's drive through FVV 101 basics. So these you've already studied. I will just rush through, because in this lecture all we want is to see where we are starting. So we're now starting, right, as far as the theory is concerned. We have the administrative background, we've got the context of significant figures, prefixes, and the rules, and the 6 fundamentals. So now let's get into the actual particle statics. So this is material that you covered, so we will rush through it in this lecture. The principles that we will cover are in chapter 2. Forces in 2 dimensions, components of forces, how we solve problems to find components of forces, equilibrium conditions in 2 dimensions. Remember, statics is all about objects in equilibrium. Then we will look at forces in 3 dimensions. Then after that, equilibrium in 3 dimensions. So this is just where I could say this is the line between your FVV 101 and FMEV 101, 102. This is the line. Basically here we did work out equilibrium, forces, and components in 2 dimensions. However, this time we are now moving into the 3-dimensional world so that we can find some vectors that are at skewed angles. So that is basically the line that I was hoping that you can identify as we go. Right, so let's look at the principles and their application and how we solve the problems. With all the problems that we will attempt during the lecture, I will give you a guide, and I'll give you a few minutes to carry out the calculation. I will not be solving problems during a lecture. I will solve the problems during tutorials where we are now cutting and dissecting all the steps and stages for us to come up with these solutions. So there are 13 principles in chapter 2 that you've done already, some of them, and some of them are new. Just a few are new. Right, so let's look at the principles that govern forces in 2 dimensions. Forces in 2 dimensions are governed by the following 4 principles. We there's a principle of finding the resultant of two forces. This principle is demonstrated by the following case. If we have a point A at which a force is acting, and that force is labeled P, and at the same point another force is acting, and that force is labeled Q. These two forces, they produce a certain effect. Q drags the object in that direction. P drags the object slightly upwards in the other direction. So when we have forces that are acting on a particle, to find the resultant of two forces, we make use of what we described before, the parallelogram rule. The parallelogram rule simply states, as we have discussed, that the resultant is the diagonal or the geometric diagonal that is formed when these forces are moved to the other sides of this parallelogram. So you can actually create it graphically to find the resultant. That is the principle of finding resultants. Now, in this text here, there is just one important item that we need to take out. So this text is just describing what we see there. The first diagram is two forces, P and Q, acting on a particle. You can draw a parallelogram. R is the what? Is the resultant. And the resultant of these two forces is equivalent to their sum. We have done this before, so this is just being redefined so that we know that a resultant is simply an equivalent force. Its effect is the same as those other two combined. So if you are carrying out some graphical method of finding a resultant, basically you just need some graph paper, you just need some reference point, you just draw some line, let's say you've got your forces, right? You just draw some line that is at the same angle as the initial force, at the same angle as the second force, and then you just measure the distance between those 2 points, and you've got your magnitude of the resultant. So that is the first principle, the principle of finding the resultant. The second principle is basically definition of vectors. So we have done this before. So vectors have certain properties. We know that vectors add up, vectors are in components. So the first simple property of vectors that's discussed here is that equal vectors have the same what? Have the same magnitude. So here you're just being reminded of that if a vector is, as long as it is pointing in the same direction as another vector, and it has the same length or size or magnitude, then these vectors are actually equal. Even though you might find one vector acting on another point of an object, the vectors that are acting on that object are equal. So vector basics are described. The second principle on vectors is that vectors are directional. So when you have two vectors that are acting on an object, if these vectors are pointing in different directions or are anti-parallel, these vectors actually sum up to 0, even though their magnitudes are the same. So this equation is basically defining what is called a negative vector. We've done this before, so you already know that as long as we've got a vector, if we know the direction in which it is acting, if it is going to be required to interact with another vector, we will simply use the parallelogram rule, or we will look at their lines of action and use either vector addition or moments. But basically, this is a definition of vector properties. Then the third principle is on addition of vectors. We've already done this before. So I'm sure you know that for you to find the resultant, you need to add the two vectors. How do you do that? So this parallelogram was formed by the initial force. So there's a force Q. Then we took this force P and we drew this force at the tip of force Q. This means that we now have a second force P, and it's an equal vector according to the previous principle. For us to then find the resultant, we would have to, if it were a distance, first of all walk from point A to point B. So in other words, you describe vector Q. Then you would have to walk from point B to point C, In other words, you describe vector P. So mathematically, the two vectors are simply summed up in that format. Respect the vector sign, please. Since we will not write things in bold, I don't think there's anyone who's got the patience to do this when you're writing. So you would just write your vector plus Q, right, is equal to Q plus P. So what we are being reminded of here is that the parallelogram rule simply introduces commutativity when you are adding vectors. In other words, Q plus P is the same as P plus Q. So that's a vector principle that is just a reminder. Then our vectors can actually operate as a lot of vectors. So we can find the resultant of several concurrent forces that are acting on an object. We can find the resultant of several concurrent forces that are acting on an object. So in figure 2.8 there, you see an example of concurrent forces that are acting on what? On an object. You have the force P, you've got another force Q, you've got another force S. So these three forces are concurrently acting on a what? On an object. For you to find the resultant of the three forces, you simply construct a polygon. So just get one of the forces, you've taken that force S, and you've just transferred it to, as long as you are connecting them tip to tail, tip to tail, tip to tail. Right, we've done this before, but it may have not been introduced basically like this. So Fig 2.8 is basically reminding us that for us to sum up the forces P, Q, and S to find the resultant, you can first sum up P and Q. So you can construct a what? A parallelogram and sum up P and Q. So you still remember this one, and you find the resultant of what? Of P and Q. Then you sum P, Q resultant, which I can call maybe R, to S. So this is the basic description that you've got the first two vectors. They form a what? A parallelogram or a triangle of vectors. Then you can say add the last vector. Mathematically, this is the same by moving your vectors conveniently as adding the vectors S and Q, right, to what? To the vector P. Hence the right hand side of equation 2.4. So these equations are basically reminding you of the basic principles of vectors. Right, that sums up forces in 2 dimensions. So this last page on forces in 2 dimensions is basically encouraging you to study on how to resolve forces into components. You've done that, you know this inside out. The first basic principle is the scalar component. So if you've got a force and you multiply to the scalar component, its initial size is force P, for instance. If you multiply it by a scalar, it's simply going to become scaled to the size of the what? Of the scalar and its initial size. If the scalar is negative, it will simply flip the direction of the force and multiply the size of the force by its magnitude. So if you are then resolving a force into components, you can do it in many directions. So figure 2.11 simply shows how one can draw one force in components. So someone can say, I've been given a force F. This force is acting on a point A of some object. You can actually construct a parallelogram by just drawing any 2 components of the force. So you can close your eyes and just plot a line, close your eyes, plot another line. As long as you then join all those lines to the tip of the vector, you've created components of the what? Of the force. So an example in part A here are components that are drawn. One person chooses to draw the component P and the component Q in those directions. So when we complete the parallelogram, we can be able to find the unknown force. Components can also be drawn in any orientation. So someone can also say this same force F can be drawn into components according to part B of the diagram. But instead of starting with my P in this direction, I want to draw my components. My first component is in that direction, the other one points in another. You will notice that this Q is pointing in more or less the same direction as the initial Q. But someone else says, okay, I will choose to draw my first component in that direction and another component in a different direction to the first Q's. So basically, this principle states that when you are given a force, you can construct its components by simply breaking it into two parts. Those two parts should reconnect as a parallelogram so that that force appears as the resultant of the two components. In fact, it actually is. So this is a principle on the resolution of a force into components. So forces in 2D, we've got an example there of finding the resultant. Problem 2.1 reads, two forces P and Q act on a bolt A. Determine their resultant. You are given the two forces P and Q, you've got the bolt. Now, one important thing that you need to get used to, engineering terms. You've already probably gone through some module that has to do with practicals or working with objects, mechanical objects. So when I'm saying mechanical objects, I mean spanners, I mean angle irons, I mean flat plates, foils, and tools, and all those mechanical objects. Pins, screws, bolts, nuts. So this module is going to point you to a lot of those objects in the question specifically. So it's important that you get to that dictionary and you revise these terms because most of them are engineering terms that you've already used before. Right, so basically this is the bolt. We don't want a situation where the mechatronics engineer is wondering what a bolt is, right? So that's your bolt A, and then someone is, let's say they fixed a rope and they're pulling in that direction and someone else is pulling in another direction. Think about it as a hook at a camp, for example. And you've got two cables or two ropes that are pulling it in different directions. So two forces P and Q act on a bolt. Determine their resultant. How would you solve for this? So the first thing is for you to just come up with a free body diagram. You've got your point A at which you've got the forces that are acting. So the forces are force P and force Q. Q is given with its magnitude. P is given with its magnitude. Obviously, with all your work, you need a reference frame. So there's a reference frame that you will draw is just relating what you've been given to the X and Y axis. So there are many frames, right? So I will just discuss using the Cartesian or the rectangular system. So you're given some angles, I'll call that theta 1, and then you're given the other angle, theta 2, and then you can list your data since that has been supplied. So the data are as follows. We've got our force P, which is equal to 40 newtons at theta is equal to, that's theta 1, 20 degrees. To what? To the plus I direction. So I'm trying to be particular, right? Then Q is another force, which is 60 newton at theta 2, which is equal to, so theta 2 is 25 degrees to the force P, That's your data. For you to find the resultant, what is the, so you already have a sketch there. And you want to now pull out the necessary equation. So obviously with this one, we said we can make use of the parallelogram law. So how do we carry out the parallelogram law? We just take one of the forces and then we just put it onto the tip of the other. The same applies to the other force. Then we find a point, let's call it point, this is point A, let's call it point B. At that point, you can now use either your graphical technique. You can take your graph paper, you can draw this to scale. So you can use a scale that says 1 centimeter is equal to 4 newtons. Sorry, is equal to 1 newton. Or maybe 10 newtons. Yeah, 10 newtons. That would be reasonable for a piece of paper, right? So graphically, 1 centimeter is equal to 10 newtons, so that you can draw 4 centimeters and you can draw 6 centimeters. Then when you plot it on graph paper, this means that you can now measure with your ruler these 2 points, A and B, so that you can find AB is equal to so many centimeters, then you convert them to newtons. That is using the graphical technique. So this is a straightforward case. You can also use trigonometry. So with trigonometry, you can construct a triangle of forces. How can you do that? Already a triangle of forces, as you can see, it's already part of this parallelogram. So you can just take the bottom part, for instance. So this already forms a triangle of forces. You've got your resultant in the center, you've got force P at the bottom, and then you've got force Q there. Then you need to use your geometry to find the angles, and you can use the sine rule to solve the problem. So this is a typical example of finding the resultant of two forces. The principles on components of forces. The principles on components of forces. This is just another summary. So rectangular components are what we will use in this module. There are several systems of reference frames. We've got the rectangular system of reference or coordinates. We've got the polar system of coordinates, polar cylindrical, and we've got the spherical system of coordinates. I suppose you've seen this in Calculus 2 where you were looking at vector fields. But in this module, we will make use mostly of our simple rectangular system so that we don't complicate things while we're still trying to grab the basics. So there we have it. We've got components of forces. The first one is giving us the rectangular components of a force. So the rectangular system simply has an X and Y axis. Origin is usually denoted by an O. And the force that you draw is in space, right? So this force is first drawn, and then you can put a reference frame onto it. So you've got your force, it is denoted by the symbol F, then that force is acting at some angle theta. That is the definition of your rectangular components of the force. How do you find the rectangular components? You then relate this horizontal component to the force, simple trigonometric methods. You can also find the components Fy, which is the vertical component, using the same angle theta, or you can use another angle alpha. So you can have fun and play around so that you can find the components of forces. Then figure 2.15 is just showing us that the system of rectangular components, it is neither here nor there. You can put it in any orientation as long as you stick to the principle. Do you still remember when we were working out in FVV 101 problems on an incline? So we've got some object and then that object is placed on an inclined plane. That plane is at an angle to the ground, and then that object is maybe moving on top and things like that. Yes. So this, oops, my apologies. Where is it? So there we have it. So this module is simply reminding us that we can use the rectangular system in any orientation. So it can be plotted as in figure 2.15, where we have the origin at O. Then we've got our force component in the x direction. And this x direction is skewed from our view, but it's one and the same setup as the first. Right. The third important component to remember are what are called directional vectors. Directional vectors are simply direction indicators. So unit vectors are direction indicators. Unit vectors are named along a certain axis. So in physics, we choose to use I for the horizontal axis, x-axis. We choose to use J for the y-axis. In other modules, you will find that maybe you'll end up using AX, you'll end up using AY. But in this module, we will stick to I, J, and K. So these are unit vectors. So every unit vector, it's a vector in itself, but it's a directional vector. It is a vector whose magnitude is 1 and it denotes a certain direction. So in other words, when you are drawing some vector in the x-axis, all it is scaling up the unit vector. So that you can say, okay, this vector is directed along the x-axis. So these are direction indicators. Figure 216 is simply exemplifying that. So figure 217 is just giving us the basics of expressing our vectors in components. So we've got our vector f, and this vector has got components in the x and y. So how do we express them? We write the x component as the letter of the vector or the symbol of the vector with a subscript x. We've done this before, so you can see that this is your fx in the I. And then that fx in the I, if you then use trigonometry, we can see from this triangle that we can name triangle O, let's say that's AB. We can tell that using the sine ratio. The sine of the angle theta is simply equal to the opposite, which is the vertical component, which we can call Fy, over the hypotenuse, which is the force or the main force F. We also have cos theta as the trig ratio that relates this adjacent side, which we can call Fx, then divided by the hypotenuse. If you then make the Fx and the Fy the subject of discussion, this is what gives you the F cos theta for your horizontal axis, Fx equal to F times cos theta. And you've got your Fy as the F sine theta. However, it depends on the angle that you use. So it's important to be consistent with the trigonometry. You can therefore write the vector Fx, right? So Fx is a component, but it can be written as a vector of some magnitude, but in this direction, which is called the I direction. Same applies, Fy is in the J direction, and so we have the total force F being a sum or a resultant of the Fx in the I plus the Fy in the J. And of course, we've got that definition from trigonometry. So this sums up the rectangular components of a force. Now, these forces can be the resultant. You can actually find it. You can actually add forces by summing their components. This is the best and most recommended method of finding the resultant. Decompose your force or your forces into x and y, and if given, j directions. For now, it's just 2 dimensions, so we'll talk x and y. So decompose your forces into the x and the y direction. Then when you're done with that, just add all the x components, just add all the y components to find the resultant. So in other words, in this example, we have the first diagram, figure 2.17, expressing the components of f in terms of unit vectors. So this is what you've already done, right? Now, if you want to find the resultant of 3 forces that are acting on a particle, the example is shown in figure 2.21. So you have a particle A. Particle A has forces P, S, and Q that are acting on it. All 3 are acting on the particle concurrently, simultaneously, at the same time. So for you to now find the resultant force on these, the idea is we need to decompose each force into its components. So let's start with force P, the longer force. Force P, the longer force, which was this one, it has an x component, which we call P in the x, and it points in the I direction. It has a y component, P in the y, it points in the j direction. If we go to force S, which is this force, which we can call S there. It is pointing to the left and upwards. So it has a X component in the left side. It's got a J component, a Y component in the upward side, or the vertical positive side. The same applies for force Q. It is pointing to the right and to the bottom, and you've got your components Q in the X and Q in the J, or in the Y. So now, if you are to add, so let's now find the resultant. So we can simply construct a simple table. This table, it summarizes the forces. So we can label it force, then we can label it, let's say X component, and Y component. In statics, it's important for you to be systematic. Don't rush to just solve. Move step by step like a grade 1. Right, the first stage, go to the second stage, have the patience. So you've got the force P, the second one, you've got the force Q, the third one, you've got the force S, and all you want is to find the resultant. So what is the X component of force P? That's your P in the X. What is the X component of force Q? Remember now, this P in the X is a what? Is a magnitude, right? It's a magnitude. So when I look at the diagram, where is it pointing? It's pointing in the positive what? X direction. Y component, it's pointing in the positive Y direction. How about Q? My X component for Q is pointing in the positive X direction. My Y component of Q is pointing in the negative Y direction. How about my S force? My S force has a negative in the X direction and then a positive in the Y direction. These are just numbers, they're magnitudes. The directions you are deciding as you see the diagram. This implies then that your R in the X is now a sum of those three X direction forces. Px plus Qx minus Sx. Then your Ry is a sum of those forces. Py minus Qy plus Sy. Then you can plot your resultant force acting on A in the X, resultant force acting on Y on A in the Y, and the actual resultant force. Right, in actual fact, it will look something like this, right? So it should reach to the tip of both vectors. Okay. So those are just principles of summing up the components. So sample problem 2.3 is giving you a chance to stretch, right? It's time, chance to stretch. It simply reads, 4 forces act on a bolt as shown. Determine the resultant of the forces on the bolt. So how do you find the forces on this bolt? So as usual, you've got your point bolt there. Then you've got the first force F2. You've got the second force F1. You've got the third force F4. And the last force F3. Reference frame, very important. So I will just sketch it here. You've got your XY, it's already given, but on the diagram you can simply make life easier for yourself so that it doesn't confuse you. So that's your Y dotted and that's your X dotted. Now that you've got all that information, it's obvious. So we need to now list our given data. What are the given data? Right, so with this diagram, it's very important that you label the forces and dimensions for every free body diagram, the forces and dimensions that are given. So I will just give these some names. That will be my theta 1. I'll give this one the name theta 2. That will be my theta 3. And you can then write your data as follows. Your F1 is a 150 Newton force. Right, so you can then write it as a vector or you can write it as a scalar. If you want to write it as a vector, you will then have to say at this angle. So I can just do that at 30 degrees to the plus I direction. My vector F2 is in 80 newtons. At what? 80 newtons at 20 degrees. Right, so I can actually say at 70 degrees to the minus I direction. my F3 force is 110 newtons in the y direction, in the minus j direction. And what? F4 is equal to your 100 newtons at minus 15 degrees to the plus I direction, right? So you've got your given data, your angles are already in here, right? Your data are shown in there. Now that you have those, then it means the next thing for us to solve this problem, to find the resultant. So to find the resultant, then, tabulate. You can just tabulate your x and y components. So for the sake of space, let me just go back and clear this, right? So this was just to exemplify. I guess you will make use of what you've already known before. So let me just clean this up and remove it. So what you will be doing basically in this calculation is to just identify the force, its x component, its y component. You've done this many times, so my assumption is you will simply ace this stuff. So you've got F1 up to F4, F3, F4. What is the x component of the force F1? You have a 150 cos 30, and this is in the positive I direction. What is the y component of force F1? It is a 150 sine 30 degrees, and it's a positive component. The same applies, the same applies, the same applies. You add all these, you get your resultant in the x. You add all those, you get your resultant in the y. Right. The third principle, set of principles, it's not the third, I think it's the upteenth, I don't even remember. Okay, so equilibrium in 2 dimensions. So this is where we are finishing off the 2-dimensional case. So there are 3 principles on the equilibrium in 2 dimensions. On this page, we're looking at the principle on equilibrium of a particle. So if you have a particle and it is in equilibrium, there are several forces that are acting on it. So for instance, in figure 2.23, the first object there, in part A, it has 4 forces that are acting on it. F1 is acting on it in the I direction, F2 in the minus J direction, F3 is at an angle in the J minus X direction, F4 is in the minus X plus J direction, right? So you've got 4 forces acting on it. So for you to solve for the equilibrium condition, if a force or if an object is in equilibrium, the sum of all forces is equal to 0. The sum of all forces acting on it is equal to 0. This means by the same decomposition rule that we worked out, this means we can decompose each force into the x and y directions. The sum of all those x forces must equal 0. The sum of all those y forces must equal 0. So one way of doing it is you can decompose this, or you can just plot a polygon of forces. So you can use the polygon law, which we discussed that time when we said you can have multiple forces acting on the same object. So the condition for equilibrium is defined in equation 2.14. The resultant of all the forces is a sum of all the forces, and it is equal to 0. Now, that resultant we've already figured out earlier, that it is a sum of all the x components. It is a sum of all the y components. This is equal to 0. So this equation is simply telling us that this resultant, or in fact, we've got the first case, right? The first case is this resultant is a sum of all forces. this sum of all forces is a sum of forces in the x and forces in the y. Then this summation can be broken down into a sum of only the forces in the I and only the forces in the what? In the j. Then all these should add up to 0. So that it implies that the sum of all x forces separately and the sum of all y forces is actually equal to 0. Right. Ideally, this is the maximum time that we will have in a lecture. So just because it's an introduction, I will give myself a little bit more time so I can finish this material. Okay. So equation 215 is basically summarizing the idea that you've got forces in the x and forces in the y separately adding to get a 0 for the equilibrium condition. Now, Newton's first law of motion is what governs the equilibrium condition. What does it say? We say that if any body or every body remains in its state of what? Of motion, or it remains stationary unless an external force acts on it. So according to the equilibrium condition, all bodies will remain in their state of a stationary condition unless an external force act on it. So which means the equilibrium condition is where we have an object that stays stationary and it doesn't go anywhere. But there are forces that are acting what? On it. If there is no other external force, it will stay like that. Your table, if you leave it at home and no one moves it, you will find it back there. So basically, that's the principle that governs the equilibrium condition. Principle number 3, the problem solving using free body diagrams. So we've already covered this a little bit earlier. You are given, excuse me, you are given diagrams that are pictorial, because as engineers you need to see what's happening and you need to see the objects and you need the regular shapes, right, so that you can tell what we are dealing with here, right? So there are 2 types of diagrams that you're given. The first one is a diagram called a space diagram. All your questions will have some 2 or 3 dimensional space diagram. It will basically have pictures of what's happening and the objects that are involved and the forces, objects on which the forces are acting. So in this space diagram, for example, you've got a truck and there are 2 loaders that are using pulleys. So there's some ropes that are hinged through pulleys, and if they pull, they can get to load or unload this truck. Hopefully it's not too heavy an object, right? But for you to analyze this now, it is best that you redraw this diagram, right? So you'll need to then, instead of you having to draw the whole space diagram, you can then come up with what is called a free body diagram. So the free body diagram has 2 important things. In dynamics, it will have a 3rd important thing, but we are in statics, it has 2 important things. It has the forces, right? And it has the dimensions. The forces and the dimensions. Those are 2 important things that we need to see on your free body diagram. Have the habit of always stating your dimensions. You can put them in, you can put the symbols that represent the dimensions, or you can put the actual values on your free body diagram. That way you can, I actually prefer to put the symbol and equate it to the what, to the value, because that way you can now do your math easily. Then you've got alternative forms of the free body diagram. So always have the habit of converting your space diagram into some free body diagram for analysis. One other thing that's important in your free body diagrams is nomenclature, right? Naming conventions. Develop a system in your mind of giving names to these tensions so that you can correctly carry out the algebra and then substitute at the last stage or at any relevant stage. An example is shown here. We've got a point A, which is the junction at which the ropes are connected. We've got a pulley B, and there is a cable or a rope that is connecting points A and B. So this textbook gives it a name, T for tension, AB for the points that are at which that tension is acting. The same applies TAC, and then the weight is usually just given a W, or you can say mg. Right, so basically, always remember now in statics, if you are dealing with weight and the question is in the imperial system of measurement, you do not write mg, because the weight is written as a force, right? So you are immediately writing the force in pounds. That's an important thing that you need to remember. So an example problem is given here, simple problem 2.4. In a ship unloading operation, a 500-pound automobile is supported by a cable. A worker ties a rope to the cable over its intended position on the dock. At the moment illustrated, the automobile is stationary. The angle between the cable and the vertical is 2 degrees, and the angle between the rope and the horizontal is 30 degrees. What are the tensions in the rope and cable? So you're given the space diagram. There are dimensions that are already supplied. Your next stage is to plot the what? The free body diagram. What do we need? The forces and the dimensions. So the relevant point, the starting point of this is, remember, we are revising particle statics. So our starting point will be some point A. At that point, we have some rope, and we will call that rope AB. Rope or cable AB has obviously some tension in it, which is a force that we can call TAB. Rope, this is our horizontal. So the most important thing, again, your reference frame. Then your second rope is someone who's pulling to it, so that will be the tension AC, right? And it's a vector. But this object has a what? Has a weight, so I'll just call it W. So there goes a free body diagram. So you've got your point A, and you've got your point B, point C, and you've got your forces acting on it. What do you want to find? You want to find the tensions in the rope. So what are the dimensions that we're given? So you're already plotting on your free body diagram that there is an angle, theta is equal to 2 degrees. So let's say that's theta 1. We've got another angle, theta 2 is equal to 30 degrees. So now we have the angles and we know the orientations. Method. Now your method of coming up with the tensions depends on your on the requirements. If they do not say that use the graphical method, then you can use your convenient method. So your data are already supplied. You've got your theta 1 is equal to 2 degrees. You have your theta 2 is equal to 30 degrees. You have your weight is equal to 3,500 pounds. Now, if we want to find the tensions in the rope, then one of the easy ways, if there are 3 forces, is to just construct a what? Construct a triangle of forces. So let's construct it. So we've got some vertical force. I've exaggerated the 2 degrees for convenience. We have some vertical force, which is the weight. Then we've got some other force that interconnects them. So the weight points downwards. The tension AB points upward. Tension AC points in that direction. I know, obviously, that this is what? This is a 90 minus what? Okay, so let's see. This is a 2 degrees, so that's theta 1. So we're happy because this is the vertical. The weight always acts in the vertical sense. So obviously we've got our theta 1 there. Then we've got a 30 degree where? We've got a 30 degree here. So which means this will be a 90 plus a 30 degree, right? So that would be your 120 degrees. So let's call it theta 3. That will be there is equal to 120 degrees. So you already have 2 sides. You've got a 120 degree side. You've got a 2 degree side, which means you can find your theta 4. When you have these, then it means you can use your sine rule, isn't it? So let's just say this is TAB, and that's our TAC, and that's our weight. So using the sine rule, we want to find TAB and TAC. So we know that this side, TAB over sine of theta 3, is simply given as the weight over sine theta 4. Then you find TAB, but this is also the same as TAC over the sine of theta 1. Then you can find your unknown T's. That covers equilibrium in 2 dimensions, and FVV 101 statics for particles is done. Now we are moving to the 3-dimensional case. We are now moving to the 3-dimensional case. So this one is very important. We start, for the 3-dimensional case, we start with the rectangular components of a force in space. Rectangular components of a force in space. This is a straightforward section because it's the same principle just applied with a 3rd dimension. So forces in 3 dimensions can be described by their rectangular components or Cartesian components in space in the following way. If we have a force acting at a point O, and this is the force F, if we are considering its 3-dimensional action, we can construct a plane. We can construct a plane by simply completing a polygon in one plane in which the force is acting. So it is at some angle. All we want is to put a cardboard on that force. So this is just a cardboard. This is just a plane. So it's just like cardboard. Now, this plane is where the force is lying. So it's obvious that if we were to draw XY axis on that plane, we've got a Y axis, but we've got a horizontal axis of the plane, which we can just call H, for example. So the force is at an angle theta Y to the Y axis, and it's at an angle theta H to the horizontal axis on that plane. This same force, however, by virtue of it being on this plane, if you were to look at it from up there, all you see is a line that is in between the X and the Z planes, axes. It is now lying at an angle phi to the X axis. This means you first related it to the Y axis, right? You related it to the Y axis. So there's an angle in the Y direction. Now that you've related it to the X axis, you can also relate it to the Z axis. So this is where the 3-dimensional analysis of forces lies. So in this example, you're given some components of this force. The Fy is the Y component of the force. So if you look at the trigonometry there, let's look at this H axis. Let's look at the Y axis. Our force is lying on that HY axis. This was the angle theta Y, which is the angle between the force and the vertical axis. So if we are to relate them, we can use the cosine of theta Y, which is equal to F in the Y, which is the force component in the Y direction, over the over the force. For this reason, Fy is given F times cos theta in the Y. That is the definition of your Y-axis component. Now, if we have the Y-axis component, this is the H-axis component. So this one was already defined. Then the H component, the horizontal component. Remember, horizontal is not necessarily X all the time. It depends. So in this case, because we put a plane in between the X and Y axis, we created a new axis. Called the H axis. That is where this force in the H component lies. So this equation 2.16 is defining the component f in the h, which is basically f sine theta y. Remember, we are using this view. So because of that, you can then relate this force to the three dimensions in the following way. So you have the force FH, which we already drew here. So it's already drawn for us actually. And we've got that angle. So we already figured out F in the Y before in this equation. This F in the X is now a component of this horizontal force, right, in the X direction. A component of that horizontal force in the X direction. This is why we have an equation which says F in the X is simply equal to the horizontal component FH cos phi. FH cos phi. Because we're now considering this plane, which is the XZ plane. So since our FH was F sine theta y, we can now write F sine theta y to replace FH, and we can write our cos phi, which was there already. The same applies. FZ is now FH sine phi, which is now FH, which is F sine theta y sine phi. In the end, you now have your force written in terms of Fy, Fx, and Fz. Fz. So the magnitude of that force is obviously just the square root of the square of the components summed together. So force is in three dimensions. The second principle is that the force is defined by its magnitude and 2 points making up a line of action. So if you have a force F that is in working, or its line of action is in between points O and A, that force has components in the X, Y, and Z axes as we described earlier. So this is an example of the X component of that force. In other words, it's lying in a plane created by the force in the x-axis, and the angle between the two is the F in the X. The second part is F in the Y. So this is still the same force, but we are now plotting the force in the plane with the y-axis. Therefore, we have this Fy. Then the same applies for Z. We simply have the same force in between points O and A. That force lies in some plane that can be created by what? By the Z-axis and the force. Then the angle between them is theta Z. So the three-dimensional box shows its angle, or the angle between the force and the x-axis, the y-axis, and the z-axis. And we have already seen how we can derive the separate components. So now, these components, if we are to think about these components in terms of unit vectors, the force F then has its magnitude F. But we know that the x component is cos theta x. We know that the y component is cos theta y, and so on and so forth. So this force at the bottom here is simply Fx plus Fy plus Fz. Fx is in the I, Fy is in the J, Fz is in the K. So basically this is just summing up the force. Then we can write it in terms of its components and factor out the F, since it's the magnitude and it is common throughout. This is what creates the start of something important that you already did, but you may have not seen it. It defines something called the directional vector. the directional vector in this module, in this chapter, is simply defined by the symbol lambda. So lambda, if you follow the math, you will notice that it is simply the directional cosines. These are the coefficients of your unit vector directions. So this lambda is actually a unit vector. It is the unit vector in the direction of the line of action of the force. Think about it this way. If you've got a force that is acting in the x direction, isn't it you call it F in the I direction? If you've got a force acting in the j direction, isn't it you call it F in the j direction? How about a force acting in between? You will now have to call it F in what? It's in lambda direction. So that direction is, you have actually done it and you've seen it before. Let me just pull out something that you have already used it in. So you were doing electricity and magnetism just now, so let me just pull this out. Which page do I still remember the page? 65. Okay, yeah. Okay, yeah, of course, yeah. Okay, so you learned about these unit vectors in basic mechanics. But there is this chapter in electricity and magnetism that shows you the unit vector. There we go. There we go. So do you still remember this equation? Still remember this equation? So this equation is an equation that defines your what? Your electric force. This electric force is acting between what? 2 points. This vector here is the directional vector. I think in one of the tats I may have mentioned something like this. So this is what is called the what? The directional vector. It is simply showing us the direction in which this force is acting. It is a unit vector. So its magnitude is what? Is 1. So if you look at this setup, this is where these forces are acting. So you've got some forces, forget about the electricity and magnetism, we're looking at the forces. So these are forces that are acting on some point. So these forces are in a what? In a certain direction. This is the what? Is the directional vector. It simply is a unit vector, magnitude 1, but it's not in a direction which is in the x, so it's not I. It's not in a direction which is in the y, so it's not j. So it's a directional vector. And we have now seen that this directional vector is actually defined. Right, so basically that's your directional vector. So this figure 2.28 is telling us that lambda has a magnitude 1. So it has the components theta, cos theta x in the I. It has another component, cos theta y in the j. It has another component, cos theta z in the k. Now, if you want to add concurrent forces that are in 3 dimensions, then there is some math that you need to do, right? So this is an example, figure 2.29. So it simply has a force that is acting in the line of action Mn. M is a point that is away from the origin. It's located at a point x1, y1, z1. N is another point into space. It has location x2, y2, z2. So there are some distances that describe the line of action of this force. So there is distance in the x, which is x2 minus x1, obviously, your distance in the z, your distance in the y. So this is a very important concept. You will use this concept even in another module next year, dynamics, and you will use it in electrotechnology, 2B. Right, so this concept defines our lambda in terms of any 2 points that are on the line of action of the force. So it is a way of calculating lambda. It is a way of finding lambda. So the first thing that you need to define for you to find lambda is the vector that defines the 2 positions. So you've got a vector, basically you've got position M and position N. So if you subtract x2 minus x1, you get d in the x. That becomes your d in the x direction, d in the y direction, and d in the z direction. So in other words, your vector Mn is the first and important vector to obtain. When you have that vector n, mn, you can now define lambda. Lambda is simply a ratio between the vector and the what and its magnitude. So for you to find lambda, in other words, or the unit vector in any direction, all you just need to do is to find the vector between those 2 points. In other words, this is the lambda I want to find. This is the force acting in that direction. So I should just find the distance from the starting point all the way to the end point. So I've got my x component, it's dx in the I. I've got my j component, it's dy in the j. I've got my z component, it's dz in the k. Now, for me to find lambda, all I do is I write this ratio. So it's my ratio of the force, of the vector in the direction of the what? Of the force to its magnitude. So what do we mean by mn? This mn we've already seen is simply a vector from point m to n. So that's why we write dx in the I, dy in the j, dz in the k. Then this d is simply what? It's simply the magnitude of which is the magnitude of this distance. So basically that is the magnitude of mn, which you can find by just taking a square root. Mn dx squared plus dy squared plus dz squared. So basically now it means you can define the force F in the direction lambda as F with a magnitude F and a direction or unit direction lambda. Now you can substitute your lambda. So this is your F and this is your magnitude, and then you substitute the direction. This then defines your ratios. So it means you now have your F in the x is simply equal to this magnitude F, which you had already, multiplied by what? The x direction over its magnitude. The same applies for the y, the same applies for the z. So in the end, when you sum up all the forces, you now know the components of a three-dimensional case. In other words, if you still remember the other hat from that chapter that I just showed from survey, it's simply equal to the other vector over its magnitude. That is how it is defined. It's the same as this lambda. Okay. So we are using lambda conveniently in physics. Right, so in this problem, basically what you are using is that principle. How do we use it? So this problem says, a tower guy wire is anchored by means of a bolt at A. So keywords for you as engineers: guy wire. What is guy wire? Bolt, you already know. The tension in the wire is 500 newtons, right? Determine the components Fx, Fy, and Fz of the force acting on the bolt, and B, the angles theta x, theta y, and theta z defining the direction of the force. Right. So we already have our reference frame. So let's plot our reference frame. So this one will be, this is in 3 dimensions, right? So it will be a difficult one. So let me annotate the diagram, So we've got our reference. Let's put this as our reference point. That's our origin. So the first thing is obviously a reference frame. So we'll put this as our x-axis. We'll put this as our y-axis. And this is our z-axis. What we want to find are the components of this force. So according to the data that has been supplied, the tension in the guy wire is 500 newton. So the guy wire is what? Anchored by means of a bolt at A. So which means we are looking at the force that is pulling from A to what? To B, right? So it's anchored by means of a bolt at A. The tension in the wire is 500. So it's obviously trying to what? To pull this upward. Now, if we have this case and the force that is acting at A has been seen. So this tension force is simply equal to the tension multiplied by its what? its directional vector. How do we get the directional vector? We just define it as the lambda, so we can just draw our lambda in the direction of the what? Of the force. How do we find lambda? How do we find lambda? Because remember, when we have this force, it's given the letter F. So let me just remove this T. Let me make it an F so that it is exactly the same as what's in the question. So they want an F there. There we have it. Right. So we want to find F, X, Fy, and Fz. We know for sure that Fx is simply F multiplied by lambda x in the I. And then Fy is F multiplied by lambda y in the j. And then Fz is F multiplied by lambda z in the k. So basically that is our force. How do we find lambda? So these will be our components. So we're already happy. How do we find lambda? The lambda vector is simply equal to, in our case, it's AB. So that's the vector AB over its magnitude. The vector AB over its magnitude. What is the vector AB? So we want to discover the I, j, and k directions. So if I'm moving from A and I need to go to B. So from this point, obviously, I need to move, let's say, in the x direction. So if I move in the x direction and I'm at that point, excuse me, so that's an arrow there, up to that point. How many meters have I moved? I've moved 40 meters. So that is 40 meters. In which direction? I've moved in the minus I direction. Right? That's my AB direction. How about when I'm here, all I want is to get what? To point B. So I move 30 meters in the Z direction. So plus 30 meters in the plus K direction. Plus, I move upward to get to point B. How many meters? 80 meters in the J direction. 80 meters in the J direction. What is the magnitude of this whole motion? It is simply 40 squared plus 30 squared plus 80 squared. Let me just see, I'm suppressing units here. Let me see if we are using SI units. Everything's in SI, 30, 40, and 80. So we have first found the direction vector, which was the AB. We are dividing it by the magnitude, by its magnitude. This is how we find the what? The directional vector. So when we have the answer to this, isn't it, we'll just get something in the x plus something in the y, right? Plus something in the j. So that's our lambda z in the k. So this is what we will get. Now that you have this, it's now a matter of you multiplying. For you to have your f, your fx is the magnitude of f, which has been given, multiplied by lambda x. So it's 2500 multiplied by that minus 40 divided by whatever you get in that square root, and then you get your numbers in newtons, and you're done. How do you get the directional vector? How do you get the directional vector? We've already seen that the lambda x is simply a cos theta in the x for the I direction. Cos theta x in the I direction. So in other words, you just make use of which equation? You make use of that equation. There's your what? There's your lambda. So that's it. That's where it all starts. It's just a directional vector definition. That's where we take the notch a little bit higher from your FVV 101. Okay, so then you can finish off problem 2.7 and you can then check with the textbook. Otherwise, this is actually what summarizes this lecture. These are the fundamentals. So equilibrium in 3D is now the very same thing that we were doing before. You are just resolving these vectors into their respective directions so that you can find the equilibrium condition. So obviously your main principles for equilibrium in 3D, as you can see in this example, for you to hoist this car in this way, you would need some forces acting in these cables. Let me change this color here to make it stand out. So you will have some force, some tension in there, some tension in there, some tension in there, some tension there. And these tensions should end up forming an equilibrium condition with the what? With the weight of the vehicle. So this means that in this practical application, the sum of all forces in the X, the Y, and the Z must add up to 0. So for you to come up with your equilibrium calculations, you need to draw your free body diagram. Resolve each of the forces systematically, each of the forces into rectangular components. So this is your definition of resolving them into rectangular components. Then you set the resultant or sum to 0, right? Set your resultant or sum to 0, and you're done. You're done with the equilibrium condition. So this is a cool example, 2.9, which simply says a 200 kilogram cylinder is hung by means of two cables, AB and AC, that are attached at the top of a vertical wall. A horizontal force P perpendicular to the wall holds the cylinder in the position shown. Determine the magnitude of P and the tension in each cable. So you already have this example here. You want to find the magnitude of what? Of P and the tension in the cable. The first simple case is for us to express our forces. So our free body diagram is going to have a point at which we've got some weight acting on this object. So there's some weight there. And in 3 dimensions, we've got some plane, we've got some vertical plane. So let's call that the Y direction. Let's call this the Z direction. Let's call this the X direction. So in the X direction, that's where we've got the force. So let me just put it as the X direction. And our force P is acting in that direction because they say it is perpendicular to the plane of this object. So we've got the force P that is acting in the X. We've got another force which is the tension. The weight is drawn already. The tension from points A to C, and then the tension from points A to B. So that's your TAB, TAC. Right. So now that you have that, for you to find, this is in equilibrium. So the sum of all forces, is equal to 0. The sum of all forces is equal to 0. So let's look at our horizontal forces. So we will just write the force, the X component, its Y component, its Z component. Right. We have forces P, weight, TAB and TAC. TAB and TAC. Okay, so we want to find the resultant and add all those to 0. The force P, we have been told that this is a horizontal force that is perpendicular to the wall. So by virtue of this reference frame that I've chosen, P only has a component in the X. So we've got Px, and it is a positive component. It has a 0 component in the vertical and a 0 component in the lateral. Then the weight is obviously pointing in the downward direction. There's a 0 in the X direction, but it has a negative, whatever value it is, in the Y. So this is the value that you can get from the mass because it's metric. Then TAB. TAB has an x component. What is that x component? So for us to get the x component of TAB, obviously we need what? Lambda in the x. So that would be that would be the tension T multiplied by, so let's just call it TAB multiplied by lambda in the x. And is TAB in the x a positive or a negative? By just inspection, you can tell that it is what? A negative force. Then in the y, it's obviously a what? A vertical force. So that's your TAB in the y. Sorry, that's our lambda in the y. Then our TAB in the z has got a lambda in the z, and it is what? It is positive. The method that we used to find lambda before is the same. Find the direction vector first. Find its magnitude and divide the direction vector, each component, by that magnitude to get these lambdas. TAC, the same applies. So we've got our TAC multiplied by its lambda in the x. So let me call this one lambda 1. Let me call this lambda 2. Right, so its lambda in the x. Is TAC lambda in the x positive? No, it is negative. Then we've got TAC. How about lambda in the y? It's positive? Yes. How about TAC? How about its lambda in the z? In the z, it's negative. Right, because it's pointing in that direction. So basically, you've defined your directional vectors and then you add them. So in the end, you will find the what? The unknowns, because you want to determine the magnitude of what? Of P and the tension in the cable. So that way it means you have, you can add these up and sum them up to 0. So, okay, basically that was more space. So basically that's it for your introduction to statics. The summary of this lecture is just that you are now working in 3 dimensions. So the principles of forces in 2 dimensions, the principles of components of forces in 2D, the principles of equilibrium in 2D, they still hold. The only addition that we have now is forces in 3 dimensions and equilibrium in 3 dimensions, and the definition of the directional vector lambda. That vector is simply the ratio of the vector directional from point A to point B divided by its magnitude. When you get its components, those components are the cosine or the directional cosines in the I, J, and K directions. So basically that sums up your first lecture in statics. We will make use of all these principles in chapter 3 from tomorrow onwards. So I wish you the best in this module. Let's jump right onto it. With this material, we are sorted to finish practice test 1. So attempt the questions and all the best in your studies. This is the end of our first lecture and I wish you the best. So enjoy and have fun.